So we've seen how to find the equation of a tangent line with a simple two-dimensional vector valued function, but let's expand that to a three-dimensional vector valued function. Now when you look at this right here, we know what that is. That's a helix, right, because cosine and sine are a circle, and it's a helix that's stretched in the vertical direction, the positive z direction, if you will. Okay, so let me just think about that for a second. So I have this right here, and if I was putting 0 in, right, 0 would get me 1, 0, 0. So it would start over here, right? At t equals 0, it's 1, 0, 0. Actually, let me write that in over here somewhere. So the starting point, which is actually the point we're interested in. So the starting point is at t equals 0, and we would put 0 into that vector valued function. So we'd have the cosine of 0, the sine of 0, 3 times 0. My marker is dying. And that would get me 1, 0, 0. Now this is the point 1, 0, 0. So I can kind of label this right here. So the point 1, 0, 0 is right here. I'm writing it in vector form when I want to think about it as a vector, but it's also the point, right? It's the vector pointing to that point, and it's also the point itself. Okay, so then I would have a helix stretching up past that, right, in the vertical direction. So it would be climbing up, up, up. Okay, so then what about the direction vector? All right, well, the direction vector I'll call that v of the tangent is r prime of t. All right, so that's the direction vector anywhere. So, I mean, I guess I could say at all places or at all t. Let's see, cosine's derivative is negative sine. Sine's derivative is cosine. And the derivative of 3t is 3. All right, so this is the tangent all along that helix, anywhere at any t value. I want the tangent at t equals 0 specifically. So I want r prime of 0. And that would be negative sine of 0, cosine of 0, 3. The sine of 0 is 0. The cosine of 0 is 1. And then 3. All right, so that's the direction vector. And this is the point. And those are the two components we need to write the equation of the tangent. Right, so L of t, and it's in vector valued form, so I'm putting a vector over my L, right, is equal to, and it'd be the direction vector, which is 0, 1, 3, times t plus, and then my point, 1, 0, 0. And then we'll change the form of that. 0 times t plus 1 is actually just 1. Then it'll be t plus 0, so that's t, and then 3t. They're both perfectly valid ways of writing the equation of the line in vector form, but the second one's the one we use the most often. So if you think about the line, you're sitting over here, your x coordinate is 1, so that's not going to change, and your y is t and your z is 3t. So you're going to have some kind of tangent line coming around like that. And of course, to get a better sense of this, we could draw them in Maple. So let's do that. Okay, so here we are in Maple. So I chose to do this. You actually can do it all in one command and tell it to do multiple space curves, but I kind of didn't want to do that. So I've got one space curve that's blue, that's the spiral, that's the helix. And then I have another space curve that's red, and that's the line. And I made it go from -2 to 2 just so we could see some more of it. And then I'm doing the display command here. So I named these two graphs, and then I'm displaying them together. And you can see there's your spiral, and there's your line. Right? So it's kind of sticking up a little bit into the air, but it's hard to see that unless you're looking at it three-dimensionally. I guess to make that happen a little bit with the graph, I'll just kind of make it stick up a little bit more, but that's fine. Right? I know it's touching at that point. All right, now, as we've seen in earlier sections, a lot of times we don't want the vector, we want a unit vector, because a unit vector can be more useful for us in terms of getting the particular length and size or magnitude that we want. So we're going to find a unit vector that is tangent to the graph of r of t equals t squared minus 1 to t plus 3 and negative t cubed at the point where t equals 2. Okay, so again, let's think about the component pieces. We need the direction vector. So we start by taking the derivative. So the v for the tangent vector is equal to the r prime of t. This would be at any t value. So I'm just going to take the derivative of these pieces. The derivative of t squared minus 1 is 2t, and then 2. And then bring the power down, negative 3t squared. We love that power rule. So this is at all t. So if I want it at the point we're looking for, at t equals 2, then the direction vector of the tangent, and one of the ways we do that at t equals 2 thing is to do a vertical line right here. So you're saying at t equals 2, which is r prime at 2, which would be 4, 2, and then if I substitute 2 into here, 2 squared is 4, 4 times 3 is 12. All right. Actually, I thought you might want to have the work there, so I just popped the work in there. So negative 4, 2, or excuse me, positive 4, positive 2, negative 12. All right. Now what about the unit tangent? Okay, so I know it has this direction. So I just need to divide it by the magnitude of it. Now you notice I'm not trying to come up with the equation of the line, right? I just want the unit vector, right, that is tangent to the graph. So this is a vector, right here, this is a vector. I'm not coming up with a vector valued function right now. So to make it a unit vector that's in the direction of the tangent, that would be equal to the direction vector in the direction of the tangent divided by the magnitude of that vector. In other words, it's r prime divided by the magnitude of r prime. Okay, so we're going to take 4, 2, negative 12, and we're going to divide it by the square root of 4 squared plus 2 squared plus technically negative 12 squared, but it won't matter because once we square it, it turns it positive. All right, what number is this? This is 144 plus 16 plus 4, so that's 164, and 164 is 4 times 41. Okay, so this is really 4 to negative 12 divided by 2 square root of 41. And now if I cancel, 2 goes into 4 twice. 2 goes into 2 once. And 2 goes into 12 6. And there we have it. The abbreviation for this, by the way, is capital T with a vector and then a little 2, right? So we found the tangent vector at 2. All right, so let's show that the tangent line to a circle is always perpendicular to the radius of the circle at the point of tangency. That sounds complicated, but it's not too bad. So let's suppose we have a circle, and the circle is radius A, just for fun. All right, so if that's the case, then we know that that circle is carved out by a function, or vector valued function, which would be a cosine of t, a sine of t. We all loved that piece in the parametric section of Calc 2, where we learned that cosine comma sine makes a circle, and then we realized that's where the whole unit circle thing was coming from in pre-calc, right? And it's still true for us. All right, so this circle right here is that R function. That vector value function gives us that circle. All right, now what about a tangent? Okay, so the tangent vector has a direction. So let's look at the direction there. So let's look at the direction of the tangent at any t value. Well, that's r prime of t, isn't it? At r prime, well, the derivative of cosine is negative sine, and the derivative of sine is cosine. Okay, so this is the tangent vector, and it has its direction. Right. Now, how do I prove that they're perpendicular? For that, you have to remember something that we learned several sections ago, which is if r is going to be perpendicular or orthogonal to the tangent vector, then their direction vectors, when you take the dot product, you would get 0. So let's find it. So let's find the dot product of r and that direction vector for that tangent. Okay, well, that means you're going to take the dot product of a cosine t, a sine t, and you're going to dot product it with negative a sine t, a cosine t. Oh, I just was able to squeeze it in there. All right, so we multiply. A times a would be a squared, and it's negative, right? So negative a squared cosine sine. So this would be negative a squared cosine t. Oh, of course it's a scalar, so there's no vector anymore. What am I doing? All right, so negative a squared cosine t sine t plus a times a is a squared sine t cosine t. Those are the same thing, but one's negative and one's positive, and therefore it's 0. And that means that r is perpendicular to v. As we learned in the dot product section, that the dot product is 0 if and only if they're perpendicular. All right, so let's put it all together. When we have a vector valued function r equals r of t, and the derivative vector r prime has the following properties. The vector is tangent to the graph where t equals 0, right? If you put in a specific value, t sub 0, that would be tangent. The vector r prime is the direction vector of the tangent line, right, to the graph where t equals 0. And most importantly, the unit tangent vector, which we abbreviate with a capital T, right? Unit tangent vector is r prime divided by the magnitude of r prime.